This video will show you some of the extensions introduced in the EAR software to be part of the Heroes runtime. EAR is a European open-source system software for energy management created at the Barcelona Supercomputing Center. It is currently used in some of the most important data centers in Europa. It has been designed to convert a data center in an energy-efficient data center. To do that, EAR offers system monitoring, job accounting, and is easy to use energy optimization. Energy is a very important constraint in current and future workflow executions. EAR is the component in Heroes controlling and monitoring energy. EAR will be deployed and executed with workflows as part of the Heroes runtime. The decisions made by the decision module will use EAR gathered data, updated over the time. For cases where EAR is not fully installed, EAR Lite will be executed. In Heroes, we must support data centers where EAR is not installed, being able to run at user mode, and also partially or fully virtualized environments. To help the decision module, we have extended the EAR reported data with pre-computed application classification. To deal with real data center security policies, data reporting has been based on plain text files that can be copied using SSH protocols. In the next slides and videos, we are going to show you how EAR can be automatically deployed and used in systems where EAR is not installed, executing then the Lite version. We will show first how EAR runs in the worst scenario, an Amazon Web Service instance 100 virtualized, where there is no access to any counter. The goal is to show how EAR will adapt the features to the context. Second case will show EAR in Mare Nostrum. In the two cases, it has been executed at user level with no privileges. The power is based on models and can be improved over the time since it is based on plugins, not affecting the core of the library. This video shows the execution of EAR Lite in AWS. In this context, EAR will be deployed from scratch and all the environment will be created based on templates. The EAR Lite feature must be enabled to support limited scenarios. When using Heroes, EAR will be compiled, deployed, and executed in the job context. We can see how the configuration is created at runtime based on templates. All the interfaces are set to dummy APIs, and the EAR library initialization detects no optimization is possible. As we can see, most of the metrics are empty or based on estimations, but the EAR library can still be used. Finally, we can also see how the Heroes logs are generated, including available metrics. Not too much in this scenario. In this video, we show how to compile, deploy, and run with EAR Lite in a real data center where EAR is not installed. The script shows modules used and the EAR Lite feature enabled for Heroes support. When using Heroes, all these steps will be done through Ansible scripts. The main difference with previous case is EAR will be able to use some interfaces and then report partially job metric. The Heroes plugin is one of the report plugins. The ear light option is activated. Once installed, we can see verify how the ear library and the Heroes plugin are installed. We have executed the following script. It has three sections. First, we load ear module. Second, we enable Heroes plugin. And finally, we run the application using the run command to load ear library and environment. Again, we have set the verbosity to the maximum to show ear actions and configuration details. We can observe in the output how the ear paths are set with local, per user, paths. In this context, some metrics and details, such as the list of CPU frequencies or the floating point counters, are available. Periodically, ear competes runtime signatures that are reported using report plugins. Report plugins can link with Myriad or Heroes CSV files. In this example, we can see, for example, CPU frequency, gigaflops per second, percentage of MPI time, I/O activity, and power estimation. After the job execution, Heroes data is ready. We can see how two folders have been generated, one for application granularity data and another one with runtime data. In both cases, there will be one file per node to avoid conflicts. In the slide, we can see data for each one of the two nodes used in the test. In contexts where ear can optimize energy, we can select one of the default policies. The best one for Heroes is minimize energy to solution. Energy optimization is divided into stages. First, ear classified job activity, and second, for computational phases, it applies energy models and energy policies. Energy policies select CPU, memory, and GPU frequencies. Next slide will show an example with a memory-bound application. The figure shows the visualization with Grafana of job metrics collected with Heroes plugin. The results are from the execution of HPCG in one IntelliSA Lake. We executed three cases for evaluation: without optimization, running with turbo, without optimization running at 2.2 GHz, and with min energy. The computation phase classification panel shows how ear classifies HPCG as memory bound for 87% of the application duration. This type of applications are typically good candidates for energy savings by reducing the CPU frequency. In this case, the reduction of the CPU frequency to 2.1 GHz has led to a total of 10 of energy savings. In a fully installed system, ear data is reported to the system database. To simplify ear utilization, ear supports the execution of jobs with multiple report plugins, being possible to report to MariaDB, for example, and to Heroes logs path at the same time. The Heroes report plugin generated per application data and runtime data. Per application data is the average of the whole execution, whereas runtime metrics will allow the decision module to differentiate between application phases, having a better job understanding. To make it easy the decision module work, the Heroes plugin already includes the accumulated time in the application phases differentiated by ear. Ear differentiate the following use phases: computational, MPI intensive, I/O intensive, CPU busy waiting periods, and applications using CPU and GPU. Your data can be visualized with different tools. One of them is Grafana. Grafana can be used for system telemetry visualization, but also for job metrics. The figure shows some dashboards created using the CSV file generated by ear. For example, the first graph shows, with gradient of colors, the node power consumption over the time. Third graph in the left side shows the total number of nodes reporting the percentage of MPI showed in the y-axis. We can see how this application, which was executed with 6 nodes, is quite homogeneous over the time. In the last 2 years, year has been extended to provide the requirements of the Heroes project. As feature work, we think it is possible to improve the CPU power models in partially limited contexts and also adapt the energy policies to these scenarios. In case of more complex workflows with repetitive patterns, we could also think in workflow optimization policies where power resources would be allocated to high priority tasks. The year code including Heroes support is currently available in the last year 4.2 public release.